So in fact, for the friend 1 meter above us and the friend 1 meter below us, we find that they accelerate along world lines that have the same asymptotes. Okay? In other words, if I'm going to do the usual thing with special relativity, to build a sort of grid of clocks and rods by sticking various observers at fixed distance away from me, those observers naturally are these uniformly accelerated observers with the same asymptotes asymptoting to the same light cones. Okay. What's interesting there is that you'll notice that although these observers are a fixed proper distance apart, it's clear that the line I draw way out here is curved much less than the line I draw in here, right, if they're the same asymptotes. Because this line in the interior has to turn very quickly from following this bottom red line to following the top red line. Whereas the one far away has much more time to execute the same reversal of direction. Right?
Does the proper length of the rope change?
No, that's the condition. The proper length of the rope remains constant.
So it's a special rope?
Well, most ropes do that if they don't break. You put a rope under a given stress, unless it gets old, it stays there and it remains the same length. So this is a very physical way to build a coordinate system. No, that's where we're going. As I mentioned, it's clear that this one is more curved than that one. What that must mean, if you think about it, is that even though they're remaining the same distance apart, their intrinsic, what we call proper acceleration, is different. The ones down here are, in fact, accelerating faster than the ones up here. Okay? And in fact, one can do a calculation, which I may choose to do next time, or may leave as a homework problem, which shows that the proper acceleration is given by, I'll put in the factor of c squared for you, c squared over this parameter c. So the closer you are to the light cone, the higher your proper acceleration. And in fact, if I look at the example that goes very close to the origin and turns around very quickly, well, it seems fairly clear that its proper acceleration is very, very, very high. So much as in the black hole case, no coincidence, one finds that if I tried to do what Tony asked me to do, to keep lowering... Oh, by the way, this is down because I'm accelerating this way. So if I throw things out the window, they tend to fall that way. Okay. If I were to try to lower below me on a rope, Tony, okay, to help me make measurements, what you see is that as I lower Tony down, because his proper acceleration increases, I need a stronger and stronger rope to keep it from breaking. And in fact, if I lower Tony all the way to the horizon, I would need an infinitely strong rope to keep it from breaking. Which is why, in some physical sense, Tony at that point will fall across the horizon and the rope will break, because no rope is infinitely strong. Okay. All right. I suspect that this is a good point to stop, and that I can start up next time with just another comment or two. Oh, yes, where I actually make this change of coordinates and then go on to black holes. So thank you very much. Any questions?
Can you transmit messages by tugging on the rope? Does the elasticity also?
As long as I have lowered you not past the horizon, as long as I keep you on this side, then yes, I can transmit messages by shaking the rope. Once I've sent you across the horizon, then I can no longer do that.
Now, the elasticity does not do anything fun.
Not for any fundamental principle of physics. I mean, yes. It may, given that the problem is becoming highly nonlinear, the rope is becoming very strained, something funny may happen, but not for fundamental principles of physics. That's right. Okay. Other questions? Actually, let me ask you the one question. Is there any property of a black hole that you've heard about which you have not seen reflected in this description? Aha! Good answer. Good answer. I will short-circuit that by saying that in the black hole case, the calculation of the temperature is somewhat hard, although I will try to get through part of it by the end of my lecture series. In the same way, a calculation for a temperature is somewhat hard here, but can be done and does, in fact, give a temperature. So this also has the thermal property of a black hole. I am not going to do that. It's possible. I think Malik Parikh has told me that he may try to do it in his lectures, which would be nice.
But he's stuck in India.
But he's stuck in India at the moment. So, well, if someone gives me his time, maybe I could do it. But I don't know what the organizers have in mind. Okay, that is a tricky thing. A tricky thing. All right. Okay, thank you.